Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is EMC interference search and measures. Our speaker is Laurent Völkel. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in the feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link for the presentation in the next few days. The recording will be available at our website shortly. So now I will hand over to our speaker Laurent, and I wish you an exciting presentation.
Perfect. So hello everybody, my name is Laurent Völkel. I'm field application engineer at Würth Elektronik, working with Würth over 20 years. And today in a very short presentation, I try to show you some measurement technique and also some EMI noise source, how to try to find the EMI noise source and what you can do against some EMC noise. So first of all, when you are looking for EMC, the most important thing is in EMC troubleshooting that you don't start your EMC situations to solve it in the EMC chamber. So when you think the EMC will be solved later in the EMC chamber, it's almost too late. You have to try to understand that EMC have to be careful and start at very early design stage. So when you make your development and you know that your DC-DC converter running at 500 kilohertz and you take care about his third, fifth, and seventh harmonics, you maybe not wonder in the EMC chamber that you need to redesign it because you don't take care about this frequency. I always say you put some investment in the development phase, which is paid back after the prototyping, that you don't have to redesign it. Everybody will ask how I can check the EMC. Good question. I know it's not so easy. It's not just a multimeter and measure it. You need a little bit more like a multimeter. You need an EMI receiver. You need an anechoic chamber, antennas, some listens, and so on. It's not that easy. I know. There are some possibility to carry on your PCB if you have a near field probe, or you can have even some nice scanner that's existing. So nice scanner where you can put your PCB and you can make a E-field or H-field sound. Company like Detectus, they're offering such devices, and you can try to detect with this in the near field what is the problem. But later you will need to go to the EMC chamber and make a real EMC measurement. The EMC failed most of them. Sometimes you have by passing the EMC by first shot. That's very wonderful. I wished everybody to have experience. I had only once this experience, and then I asked the guy if this machinery was switched on. But later you think about put some ferrites on the cable, and for these different cables of different ferrites which you can put on the cables, you can use different materials. You can use nickel zinc, this is the most used one. You can use magnesium zinc, this is a little bit more efficient in low frequency. If you have less than 1-2 megahertz noise, you can use manganesic zinc. If you want to have a very large bandwidth of frequencies, starting from few hundred kilohertz up to hundreds of megahertz, then you can try to use these nanocrystalline cores. which are expensive but have the most bandwidth. What happened in fact with this ferrite core, what they are doing for this EMC noise, they are not absorbing or something like that. They just take this energy, which is electromagnetic energy, which are generated, the bad electromagnetic energy. And in physics, we have a law which means energy never get lost, always have to be transformed in different form. So actually the ferrite core transformed this electromagnetic energy into the heat. You have a vector of E field and H field to each other, and this electrical vector and magnetic vector get this ferrite core to be magnetized, demagnetized, and in this eddy current losses and these magnetizing losses, border domain is changing inside, taking to generate heat. But believe me, even if you take a good Fluke thermal camera and you look on your ferrite core, you should not see they're getting very hot. When your EMC is that much that you make the ferrite core hot, I always say this is not EMC problem, this is the safety problem. Run away fast you can. In automotive, you can get them hot when you make this 400 volts per meter immunity test, but normally in a radiator emission should not be that like that. Well, sometimes it can happen that you're doing a good EMC job in your device and you put EMC plus EMC devices, both are tested and certified together, and then you find out, by EMC, that doesn't work. What you can do in this case, because you can not do anything more because you fulfill the EMC, the other component or block or device is not yours, is a purchased one, and you have to connect both together. The only one way is to put something between these two wiring or connection to try to make an impedance to keep this noise away from your device if your device have an immunity problem or when the system have an emission problem. So the only one thing what you can do, try to put some filters or ferrites on these cables. Uh, the most important thing is when you're aiming and try to solve EMC problem, it is the first thing what you have to do to recognize which kind of coupling do you have, because this kind of coupling could be common mode noise or differential mode noise. So this is very important to find out before you talk about components or whatever. If you don't know that, it's a lot of try and error and a lot of redesign, believe me. How you can find out common mode or differential mode, I can give you a hint. When you have a plus minus power supply, you can take these both wires together, plus minus together, put a ferrite on both wires and look what happened. If you reduce the noise or you increase the immunity, you have 100% the safe that you have a common mode problem. You have a common mode noise, look into the spectrum of the EMI measurement machine, and for this spectrum, take a common mode choke in this plus minus line and use for the maximum peak a right common mode choke and solve the problem on the board. If this plus minus wire with the ferrite did not help at all, no change, zero change, it doesn't mean the ferrite is not good enough and you need more ferrite. You should have maybe a problem which is not common mode, it is differential mode. And only for testing, you can do one thing. The trick is split the wire, put one ferrite on plus, only for testing, one ferrite on minus. And if you have on both wires now, each one ferrite core, it means you have a differential problem if this solution helps. When your ferrite is not powerful enough, you can try to put more ferrites. And when you put such more ferrites on the cable, and when the cable is not long enough to put more ferrite, you're doing something wrong. That's definitely not the right way. So this is the only one way if it's a wired system where you can try to define common mode or differential mode. If it's a differential mode noise, the cheapest solution is of course is that kind of cheap bit ferrites which you can place directly, pick and place SMD on the PCB. Check the maximum current on that. That's very important, and then you can decide on your size which fits in the PCB to put the right component. When you apply a ferrite, a snap-on ferrite or a toroid or a sleeve on this cable, like plus minus cable, you have to think about if that's the solution and you still want to make a redesign. Be aware that you are working about and talking about a common mode choke. Even it's just one turn, but it is comparable with a bifilar wounded common mode choke. The problem is that 99% of that split ferrite or snap-on ferrites are made from nickel zinc material, and 99% of common mode choke are made in manganesic zinc. So already you have a problem of the bandwidth. It won't act in the same way, in the same frequency. So check the core material of the common mode choke. You should use as well a nickel zinc core. And if you have only one turn, by one turn you have maybe 5 microhenry. You don't have this big 5 millihenry inductance, which mostly people try to use it. No, you have to look on small values. Even if it's a ferrite core nickel zinc and you have 10 turns, you don't have 1 millihenry there. You are talking about hundreds of microhenry, and that's it. That's the maximum what you're talking. Where is the EMI noise source? Well, yeah, there could be from different stages. Like I took here some power supplies here, like a SAPIC or Zeta topology. They are most used today because if it's something battery powered, you have a buck boost option in this case. The thing is that you have critical loops and you have to filter the input and output. In buck mode, you have to filter definitely the input, and as soon you talk about boost mode, you have to filter and think about the output of this DC-DC converter. The Zeta topology, it is a little bit quite similar to the SAPIC. The only one difference is that the switch and the inductor is in a different position. uh, by Zeta topology, you have to filter definitely the input because this is quite very noisy. And if you talk about SAPIC topology, you can see here now is swept the inductor and the switch, the MOSFET. You can use an output, a good filter, and that's quite okay. You don't need to put two different inductors. You can use one double choke inductor with bifilar wire wounded one, and you can use the same core material and one single bobbin, and you put two different turns on it. You have 4 legs, and you can use in SAPIC and in Zeta the same one inductor with a double winding. It's not necessary to put two separately inductance. About the polarity, it is important to take care because this is crucial, and then you can make a nice buck boost converter. But let me check a buck converter, a simple buck converter. What you're doing, in fact, in a buck converter. First of all, you come with the current and charge the input capacity, and then from this capacity, from the input capacity through a switch and the inductor, you put the energy in the output capacity. So actually, you transfer input capacity to the output capacity. The most dangerous path, it is the input capacity ground, the diode, and the output capacity path. This PCB track should be not made from auto routing. Don't push the auto routing button. Use here your manual routing and put it in one single very low impedance layer, because this is, if you take a near field probe and you go close to this area, you will see this is the most energy emission EMC problem area. Additionally, if you know your input capacity, if you know that is also not the ideal one, that's also parasitics like ASL and ASR. If you know the values, if you know the parasitics of your input lines, you already can pre-estimate which kind of noise you can expect in conducted emission. Additionally, when you look with your scope on the switching node, you will see that it's not the ideal rectangle signal. It is overshotting, ringing, undershotting, ringing. Where it comes from? Because this resonance circuit happening because of the diode. If you have a diode instead of a synchronous buck, it has also parasitics. Output capacity have also parasitics. The inductor has also parasitics. This high frequency resonance circuit, it's happening here between the output capacity and this diode. You can avoid this overshot and this ringing in case you will use a MOSFET and you make a synchronous buck, so you emulate an ideal diode, and it will be less high frequency ringing. And if you have a good low ASR capacity and you put not only just maybe one, you can put two of those in parallel, you can make even much better ripple resistant output. If you talk about input capacity, many people realize that I would use a X5R capacity and don't realize what is actually this X5R. X means nothing else, just the lower temperature limit. The R, the 7, or 5 means the upper limit, and the R means the tolerance. Of course, there are different dielectricum, but taking consideration that these different dielectricum, they also have a DC bias dependency. If you use an example of 25-volt capacity with the same value, you may have with a Y5V capacity by 25 volt 80% drop of his initial value. So if you count 1 microhenry, you don't have anymore 1 microhenry, you have just 200 nano in this case. If you have a X5R, it will drop 70%. If you have a X7R, it will drop 30%. Only the NP0, it is very stable in voltage, and only, of course, this is the reason why it's so expensive and more expensive, like the X5R or X7R, and it has always the ceramic MLCC of voltage dependency. Everybody, even Würth Elektronik, we measured them at almost a very low voltage, and of 25 volt or 50 volt means the maximum voltage which can operate. But it doesn't mean that at maximum voltage you will have always the 100% of his initial value. Take that in consideration. Additional, the package is also a crucial role. So everybody go to downsizing, but it's crazy because the package is also crucial, even it is the same the electricum. You can see here all these X7R capacity, all of those are 50 volt, 1 microfarad. And you can see only because of the size 0805 to 1812, they have different DC bias versus curve. The DC bias voltage influence because of the size. It's a big difference if I have big plate for my capacity or I have very small plate of 0805. So I did not compare with 04 or 2. Okay, 1 microfarad is quite high value, but 06 or 3 is existing. It makes absolutely no sense because the drop is huge, huge. If you have the place, don't go by downsizing because you may have some problem in the voltage, definitely. They are 50 volt capacitors. If you compare now 0805 with 0603, you can see here the X5R and X7R, how crucial that is. By using the 0805, X5R or X7R is not a big difference. If you go by 0603, again, the size and the dielectricum get to be very crucial, and even is 25 volt by 5 volt. You look on that. X5R 0603, 25 volt, only by 5 volt DC bias, you already lose 30% of his initial value. So pay attention about this issue. Additional, when you are using a DC-DC DC-DC converter and you have an output capacity here, example, it's an aluminum electrolytic capacity, 16 volt, 47 microfarad. It has an output voltage of 5 volt, 1 amp. The switching frequency is 1 megahertz. And if you look with the current clamp, and you can see the voltage ripple also here, you can see the voltage peak to peak delta voltage is 400 millivolt. Just take a soldering iron, desolder this aluminum electrolytic capacity, and solder instead of aluminum electrolytic capacity another dielectricum it calls polymer. Also 16 volt, also 47 capacity value, but in this case it will drop from 400 millivolt ripple voltage to 50 millivolt ripple, only just because of the capacity. And this is quite a good improvement. And you can even improve on the same DC-DC converter, take out the polymer and put now, instead of polymer on the same pad, we was clever enough to make the pad big enough and small enough to put the MLCC in 1206 size. Also 16 volt, also 47, and now the spikes go down to 40 millivolt. From 400 millivolt spikes by electrolytic goes down to 40 millivolt. That's a big improvement. How to measure that? And how to compare this measurement, how we can do that in our own setup, own small laboratory. Not everybody have 500,000 euro for building our own EMC chamber. So how to measure it? First of all, this is a buck boost converter, 100 watt. It has input filter, common mode choke, output filter, and another common mode choke as well. And it was switching frequency was 400 kilohertz. And the customer go to the EMC chamber and measure first without any filter, conductor emission. You can see here, no filter at all. And then desolder this junction to have a right measurement on input, and then measure with the right listen and also with the input capacity, the common mode choke, and actually it's a P filter, not only just the input capacity, and then he fulfill the EMC in the EMC chamber. Then he goes into radiated emission, measuring from 30 megahertz to 450 megahertz. It was already passed, but without filter. But we saw that there are some peaks here in this area, which was later discovered it was for the Schottky diodes. The Schottky diodes legs was who making that noise. But anyhow, after he connect the output and input common mode choke, the EMC level was quite good, more like 10 dB distance, and passed the EMC test also in a radiated emission. Now, how to try to reproduce that at home? Not everybody have EMC chamber and all this EMI measurement machine, but maybe you have a good scope with a very fast FFT, or you have a nice spectralizer, and you can buy this NBB21 from Würth Elektronik. It's a quite very nice, simple listen. If not, I will show you a schematic how you can do your own listen. If you want to make your own listen, it's also not a big philosophy. And then try to reproduce this measurement from the EMC lab, which was quite big peak, 85 dB microvolt here. And with the FFT and the NBB, we did measure 80 dB microvolt. The second peak was there, the third peak was there. Okay, here was already not so clear, but definitely the big peaks, you can hunt them and you can find them. And the only one thing, if you improve this, you just have to improve 5 dB better to be accurate, because you need this safety distance additional, this measurement error to the EMC chamber. That was without filter, with filter. So activate the filter. In EMC chamber, we did measure here 56 dB microvolt, 53, 49 second peak, 49. Wow, I was not expecting that. I was really impressed how this fast FFT from this RTO was working quite pretty good. Then we make a measurement. Okay, this time it's a little bit cheating, because in the EMC chamber, we did measure that with this anechoic chamber absorber with the antennas. We did not have antennas, but we say, okay, the listen is going up to 500 megahertz. Let me see if I can see these peaks that could be here. Here I cannot see it. These peaks could be somewhere here. So you can try to reproduce that by conductor emission, what is measuring actually the radiated emission antenna. And with different filter, oh no, this was a design A, this is another one. Design B without filter, that was what I showed you before. You can see here, this is already the noise floor from the machinery, but that you can see here. It's quite very clear here, not so clear, but anyhow, this could be improved in this case. And when you improve the filter and you put the filter on, you have only just the noise from the machinery, and you can see only just little bit some mountains here which is moving. That's maybe that, and this is maybe that. This is not a really distinguished, because you reproduce now not the same thing. You just try to understand what is happening with the into the conducted measurement, what is you can project to the radiated emission. Some measurement technique. Well, measurement technique, I can tell you can reproduce this kind of listen quite easy. In a CISPA 25 standard, it's even described. You don't need a big philosophy for that. You just need a 5 microhenry inductance. I did build myself. The whole system is less than 10 euro. I put that in a metal box from Fisher. The 5 microhenry I decide for inductance has a rod core inductance with a very, very uh, late resonant point to have a good bandwidth. For the 1 microfarad capacitor, I did not put only one. I put here more like 3 pieces in parallel to achieve round about 1 point something microfarad. For the 50 ohm resistor, I don't had a 50 ohm resistor, but I had 100 ohm SMD resistor. I glued them together. Soldered together this 2 times 100 ohm in parallel. So I have my 50 ohm resistor. I put here a BNC connector, the 100 nanofarad high voltage capacitor I choose here, and even without PCB soldered in air by wire in the small box with the BNC connector, perfect solution. If you want to measure microvolts, I highly recommend use this spring on the front of your tip. Don't use this pigtail, this crocodile, because this is already a wire antenna. You can try to make a short with that, and you can try to turn around your device, and you will see that it has a big influence already. So don't use this crocodile pigtail. Use this small spring on the tip if you want to measure microvolts, especially on the capacitor per voltage. Some other design tools which you can use them. It is very simple. If you use this kind of Red Expert tool, I can tell you in a Red Expert you have really measured values. Everything what you can see in the Red Expert is measured, is not just simulated, and you can see the real losses of the core losses. You can see the really EMC. You can put the system impedance. You can change from 50 ohm. You can go down to your 10 ohm or 1 ohm system impedance, because all the data sheets is always in 50 ohm system impedance. But not everybody have a 50 ohm in his application. Like a DC-DC converter, you will never have 50 ohm. But you can go down by the system impedance when you go to the Ferrite decision, and you can see which Ferrite has a good response in this frequency. Additional by LT Spice, which is now at analog device, you can download this LT Spices for free. You have also a library, and in this library you can find even Ferrite beats. Z in bracelet I device is a Ferrite beat with DC bias impedance load. So you can see what happened to the Ferrite beat during you apply this 3-5 amp, which is a really measured value. It's a good model which is reproduced from a network analyzer with a DC bias load, and you can see the saturation point also of the Ferrite beat. Sometimes you just put the Ferrite and you see that the Ferrite have no effect. Maybe you use a 0603 small size with 3 amp, which is have effect, but not the 3 amp. The 3 amp, it means because the DC resistance is so low, he can withstand 3 amp. But if he doesn't have meat, if he doesn't have ferrite around, which is saturated by 1 amp, you might have a problem. So maybe you can choose another bigger one, 18 or 805 or 1210 size, which have a little bit more meat or more ferrite around and doesn't saturate so fast and have then a good influence. I can recommend these books. The Trilogy of Magnetics is one of the 5th edition already. The LT Spice book is also good. You can see how the models have been made. You can make different good simulation. I know one doctor from University Hanover. He can even simulate with LT Spice ground planes. I was really fascinated when I saw how much effort he put in LT Spice, and he was able to make ground plane simulation. Crazy. Conductor emission you can measure. So now I will go to the question section because I will run out of time else. I will open the questions and see if anybody tries to put any question.
So thank you, Laurent, for your interesting presentation. So yes, like you mentioned now, we can just have a look in the question window to see which question come in. So maybe we start with the first one. Which ferrite core can I use for 10 megahertz noise?
Thank you for this question. Yeah, there are different materials. For 10 megahertz, nickel zinc is not maybe the best option. You can try with this magnesium zinc. And if you still have need to, if you put too many turns on the ferrite by magnesium zinc, you can try mangan zinc. Mangan zinc will be my definitely my suggestion. Nanocrystalline will be expensive if you have no budget problem. With a nanocrystalline, definitely you have the best option, but money.
Okay. So one attendee asked for more details to the Schottky diode generating the issues in radiated emissions. Can you give some more?
I did not prepare the picture, but it was definitely the Schottky diode's legs was the routing not the best way made, and we find out with a near field probe that the Schottky diode was the reason for that. Changing them in another routing and make the PCB tracks shorter, or we did reduce also these peaks.
Okay, great. So there's one more question. What is better to use, oscilloscope FFT or spectrum analyzer?
Well, thank you also for this question. Yeah, it's hard, difficult to say because depends on your budget. If you have a good budget for a scope and you have a good scope with 1 GHz with a very fast FFT, real-time FFT, then you can do with a scope also good job. Um, spectrum analyzer is always a little bit less expensive, but it's a second instrument. So if you have a spectrum analyzer, it's always mostly if it's a good fast trace, it's a good option. But right now, I did compare from the same German company to not make too much commercial. I compare the scope with the fast FFT with the um, spectrum analyzer for the same company, and even I saw that the scope is even much faster and most correct. But by scope, always if you look for 1 MHz signal, you need at least 10 times higher bandwidth. So if you look for 100 megahertz, 1 GHz is minimum bandwidth. Minimum bandwidth. If you look for 1 GHz signal and you think that you have a 1 GHz scope, forget that. You will need a 3 GHz scope for sure. And 3 GHz scope, I don't know how many of you will trust to go today after this webinar to your boss and say, "Hey boss, I heard from Laurent, I need a 3 GHz scope." He will say, "Take the money, buy a Porsche."
Okay, thank you. So the last question is for ESD suppression is to use a Zener or a varistor?
Also good question. Thank you. For ESD, I will use definitely no Zener and I will use no varistor. I will use a TVS diode. TVS or ESD suppressor with very ultra low capacity to be fast response. ESD is not a big power. Normally, it's always just high voltage and fast discharge. And for this reason, I need something very fast. TVS is good and ESD suppressor is good. But varistor are too slow. And Zener,
Okay.
not the best, not the best. I can see another question here. Somebody asked, uh, but on the other side, 0805 comparing to 0402 has higher inductance. That is almost sure you talk about capacity. It's correct. You have a higher ASL. That's much higher ASL, yes. If you don't want to talk about gigahertz filtering, I will go by 0805.
Okay.
I don't see that so big crucial issue. So I hope in a very short time I give you some ideas, some hints, and the most important thing from my side when you have EMC issue, it is, I can really tell you from my over 20 years experience, you should never give up. There's always a solution. If you fight against EMC, there's always a solution. If you try to call us, try to call our FIEs colleagues, or you can try to call our field sales colleagues, and they will try to give you the best hints or to try to help you. And if you want to be in touch with me, also you're welcome to watch my videos on YouTube channel here, or to be in touch with me on LinkedIn or Twitter. You're welcome to be in my contact list. So
Thank
thank
you,
you for
Laurent.
everybody.
Seems like you received your first phone call a minute before.
Yeah,
So,
somebody is doing today a lot. He's very, very persistent. Yeah.
so now we have finished with this presentation. If there are any questions left, we will answer them via email afterwards. Thank you very much for your attention, and I hope you enjoyed our presentation. This is the end of our digital days. You missed one presentation, no problem. They will be available at our YouTube channel. Thank you for joining. Take care and goodbye.